Let's think about the fundamental theorem of algebra. It says the following. If f of x is a polynomial of degree n, then you could actually write f in a special form. You could write f of x as some constant a times x minus c1, x minus c2, all the way up until I get to x minus cn. So c1 through cn, these are complex numbers. They're complex roots or zeros of your function f. So what the fundamental theorem of algebra says is that any degree n polynomial can be factored into a product of n linear terms. So you don't need squares or cubes here. You can always fully factor any polynomial of degree n. Let's see some examples of what this means in practice. So let's suppose I have 2x squared plus 2. Let's write it in this form. So 2x squared plus 2, I could factor out a 2 and get x squared plus 1. And the fundamental theorem of algebra says I can factor any polynomial into degree 1 terms only. I don't need a squared ever if I'm permitted complex numbers. So if I'm allowed to use complex numbers, I can write this as 2 times x plus I times x minus I. Let's do another example. What if I had 4x squared minus 3x plus 1? Well, the first thing I can do is factor out the constant that's in front of the highest degree term. So I can factor out a 4 and have x squared minus 3/4 x plus 1/4. And at this point, I can now use the quadratic formula if I choose. The quadratic formula tells me that the roots of this quadratic polynomial are x is 3/8 plus or minus the square root of 7/8 I. So you can use the quadratic formula to find this, meaning I can factor this degree 2 polynomial into linear terms and have 4 times x minus one of these roots times x minus the second root. Okay, let's do one other example. If I have x to the 5th plus x to the 4th minus 2x cubed minus 2x squared plus x plus 1, then you can try a bunch of things. You could factor it. I actually worked this example out ahead of time, and I discovered it was x plus 1 cubed times x minus 1 squared. This actually does satisfy the form that you're shown in the statement of the fundamental theorem of algebra, because I have 3 terms that look like x plus 1. So x plus 1 times x plus 1 times x plus 1 times 2x minus 1 terms. So these complex roots don't all have to be different. I'm showing you an example where you can have a repeated root. When this happens, you say that the root has a multiplicity. So for example, there is a minus 1 root or minus 1 0 with multiplicity 3, and you could say 1 is a root or a 0 with multiplicity 2. Okay, so here is an observation about the fundamental theorem. If f of x is a polynomial with real coefficients. So you're only permitted to have real numbers as coefficients, like in all of these previous examples. And if you get a complex root, a plus bi, so a and b are real numbers, and I get a complex 0. So if this is a root or 0 of f of x, then so is the complex conjugate a minus bi. So recall the terminology. This is the complex conjugate of a plus bi. So what I'm saying here is if you completely factor your polynomial, you get one complex root, the complex conjugate must be another root. It comes from the idea that you can get squared terms to factor using the quadratic formula, and when you use a quadratic formula, you have a plus or minus term in there, so you get both a plus root and a minus root, and there's no other way to do so. Let's do an example. So, for example, if I have x to the third plus 2x squared plus 5x, I can factor out an x, so I get x times x squared plus 2x plus 5. Then on this term, you use a quadratic equation, and when you use a quadratic equation, you get both the plus and the minus complex roots. So then this can be factored, if you use the quadratic equation, into x minus negative 1 plus 2i times x minus negative 1 minus 2i. Let's finish this video with one other example. How about if I asked you to find a polynomial with real coefficients and roots or zeros given by 1, negative 1, I, and let's say 3 minus 2i. So the easy way to do this problem is by just writing your polynomial in this form. I'm telling you information about the complex roots. So one of the terms must be x minus 1. Another term, x plus 1. Another term, x minus I. Now, since I said I want a polynomial with real coefficients, this last observation points out that if I have I as a root, then I must also have negative I. So x plus I. Similarly, I'll have x minus 3 minus 2i times x minus 3 plus 2i. So these have to come in conjugate pairs. And if you'd like, you can factor this whole thing out. You can expand and multiply. Let's see if I can do this in my head. So I think I might get x to the 6th minus 6x to the 5th plus 13x to the 4th. Let's see here, multiply, minus x squared plus 6x minus 13. So you can check my work on that, but I'm pretty sure I'm right because I did it before the video and I pretended to do it in my head. So this is a video that discussed the fundamental theorem of algebra. The key observation is that any polynomial of degree n can be factored into n linear terms. Okay, nice.